cut is equal to P minus profit. Minimize then the cut S star of min value has maximum profit. That's all. Because if I have two things that sum to a constant, if I minimize one, the other one automatically.
Well, what's the thing? The first cut of S comma V.
So a cut is always defined between a set and its complement.
Yeah, V, that is V.
V minus S. V is the set.
Okay.
So in other words, the min, the arg min over cut of S V minus S is equal to the arg max profit of S. It's not a fancy way of saying it. And that's the thing I was warning you about. You have to watch out for this. That we're trying to maximize something, but I'm saying you should use min cut. So you have to look for this trick somewhere which is going to flip around. Yes.
So, but then to find a min cut, we go back to the find a maximum flow.
Exactly. Correct.
So once we have the
Max flow.
I mean the graph defined clearly, then
You find a flow.
we just use an algorithm like
Ford-Fulkerson. Find the max flow, and how do you get the min cut after that? Once you find the max flow, do you remember?
min cut is equal to max.
No, the value, but how do you get the actual set? Once I get the max flow, how do I find the actual set? Do you remember this from Ford-Fulkerson? So in Ford-Fulkerson, remember you keep pushing augmenting paths, right, to the sink, and at some point you can no longer push any paths, you can't reach the sink. The set of things you can reach is your cut.
The set
Of things you can reach from the source, which does not include the sink because there are no more augmenting paths, is in fact your cut. Because that's how we proved that Ford-Fulkerson is optimal. What we said was, to show that Ford-Fulkerson was optimal, we need to find a cut whose value equals the value of the flow that the Ford-Fulkerson algorithm produced. What is that cut? Oh, let's just look at all the vertices we could reach from the source. By definition, this cannot include the sink, and that's your answer. So take your graph, augment it, run your max flow, look at the result, see which vertices are reached from the source. These are the projects you should execute.
So those vertex belong to the S.
The S side, yeah. Right. Magic. Other questions? So you're going to be doing a lot more of these as time goes on, right? In the assignments, you're going to be doing this kind of a take a problem, translate language and flow. So for flows, it was not too hard. You were all able to think about this last time, and so there the recipe is simple, right? So you have flow, you have choices. Okay, choices might correspond to edges being 0, 1, and you put directions. For cuts, it's a little bit more ingenious. You have to be a little more clever. But remember, the clue is if I want to find a subset of things, that's usually a clue that I had to think of the cut version of the problem, not the flow version of the problem. It's not a rule set in stone, but it's a good guide. Okay. More questions? And remember, even in this case, you have to show, so I haven't finished this, right? So you have to show that the reduction is correct. So in this case, let me before I answer your question, let me just get to that, right? If we computed a set of projects of maximum profit, right? We can go look at the graph, and basically this equation tells us that this will be in fact the value of the value of the cut will be P minus the maximum profit. It will be a min cut. Similarly, if we do find a min cut, we return the set of vertices on one side of the cut. That will have maximum profit. So in all these cases, the proof that these two things are equivalent is quite simple once you have this nice equality here. In general, it might take a bit more work, but in these cases, it's actually quite easy. And yes, now I can take a question.
Never mind.
Okay.
What is this notation? R of P minus?
Oh, so if you're so basically it's saying so min over this is the value. Arg min is the thing that gives you that value. So the min is just the value of the cut. Arg min is the set that achieves that min.
Okay.
That's all. It's just sorry. I should have mentioned that. It's a shorthand for saying I want the thing that achieves the minimality. I don't care what actual value. Because we're saying the thing that achieves minimality here is the thing that achieves maximality there, and in fact the two are equal. Okay. If there are no more questions, we move on. Okay. I don't normally like to do this, but I'm going to do it because like it's the most like fun topic in this class, I think. So I can't resist the urge to tell you all
This is
about it.
exciting.
Huh?
It's exciting.
Yes, it is.
Well, it's gonna end like a cliffhanger though.
Sorry?
It's gonna be a cliffhanger at the end of class. You're gonna introduce it.
That is my goal. To hang you all off cliffs. We're now going to talk about a whole class of methods that really supercharges your algorithm design ability. Right? Everything we talked about so far is very powerful. But once you throw in the ability to toss coins in your process, then life becomes very interesting. And so it just will blow your mind. Let me give you an example. Here's a problem. You're given an array, and you're told that n over 2 of the entries in this array are 0. How do we solve this problem? No trick. There's no trick here. No tricks, I promise you. Solve this problem. What do I do? No tricks. It's like a CS 101 kind of question, right? How long will it take you to do this?
Is the array sorted?
Huh?
Is the array sorted?
Did I say so? You can sort the array if you want. Would you like to sort the array? Okay. So how long will it take? Huh? Take your time. That's not acceptable. I want you to do this constantly. Many times it's too slow. Many times it's for people who wrote code in the 70s. We're in the big data era. Many times it's slow. No, it's true actually. Many times it's very slow. It's not good enough. 10 is a billion, you can't spend like half a billion times finding it. So here's an idea. Here's my algorithm. Pick an index at random and look at it. Is the I 0? So hey, I got lucky. That's your answer. Takes one. If not, I try it again. This is an algorithm of kind. What is this running?
So the worst case will still be vegan.
I don't know.
Huh?
I'm gonna say the worst case we can keep picking the same thing over and over again. Right?
You could, but I'm saying to pick it at random so that somehow feels like it's missing the whole point of picking at random. The whole point of picking at random is that that thing you described, that you just keep picking the bad thing over and over again, seems unlikely to happen. But how do I even talk about that? What does unlikely mean? I mean, you're doing worst case analysis. So let me ask the question a different way. What is the expected running time of this algorithm?
Time taken to cover all the elements by
No, let me say this. What does it mean to ask for the expected running time?
It means that I'm able to pick all the zeros
No. I mean, more basic question. What does it even mean to say expected running time?
On an average.
On average of a what?
So
Huh?
if I repeat my experiment like multiple times,
Yeah.
what is the valued convergence?
So in other words, you run the algorithm till it stops, write down its running time. Run the algorithm till it stops, write down its running time. Run it a gazillion times, take its average. Because that's too much work. Can I formulaically sort of figure this out without having to actually do this simulation? What would the expected running time of the algorithm? Okay, so let's ask the following question. What is the probability that this algorithm stops in one step?
0.5.
Why? Because
Every other.
Because half of the elements are promised to be 0. The probability of picking one of them is half. So it's probably 0.5, I'll stop in one step. Okay? What's the probability of stopping in 2 steps? 0.5? Why? The probability of stopping in 2 steps, you have to be careful here. I mean, this is not Stephen Colbert. All probabilities are not half.
I don't think I've done this in a while. So.
That's fine. Let's see, how do we think about this? Well, the probability of stopping in 2 steps is the probability of not stopping in the first step times the probability of stopping in the second
1
step.
over 4.
1 over 4. Okay, what's the probability of stopping in 3 steps? Huh?
1 over 8.
Yeah.
1 over 8. In general, what is the probability of stopping in k steps? So the probability of stopping in k steps is 1 over 2 to the k. Right? Okay. What is the average of the random variable that captures how long this will take to stop? If I tell you, well, 1 occurs with probability half, 2 occurs with probability 1/4, 3 occurs with probability 1/8, what is the average value of this random variable? The average value of this random variable, in other words, the expected running time, is equal to 1 times a half plus 2 times 1/4 plus 3 times 1/8 plus so on. In general, it will be the sum over of k divided by 2 to the k as k goes from 1 to infinity. Okay? Now this takes a bit of work to figure out what this is going to be. And we're almost out of time, so I will leave that for next time after the spring break. But you can show that the expected running time of this procedure is basically going to be something like so in expectation, on average, this algorithm will find an answer in 2 steps compared to your n over 2 for deterministic algorithm. But of course, this is an expectation. Maybe I get unlucky. That's a different story. And in fact, what we will go on to do is say, well, yes, the average is great, right? You know, the average salary in the US is, I don't know, $2 million something. But if you throw Bill Gates out of it, you know, what is the distribution of this number? Not just the average value, what is the distribution? And in fact, we will be able to do things like that as well. We will show how to give you the distribution of the behavior as well. That's another story. But the point I want to make is that in this simple example, and we'll see more like this, the ability to randomize allows you to do things like searching and other kinds of problems way faster than any deterministic algorithm ever could do. And so that's why we're going to learn more about randomization. So I will give you some refresher notes on probability. Okay, I think none of you probably have done the probability in a long time, so you're gonna have to refresh what it means to be a random variable, what is expectation, what is dependence, what is variance. I'll give you some stuff to read, and we'll be using those concepts as we go along. But this will bring us to a much more powerful tool, and I guess I'll see you after spring break. Okay.
I made a mistake on Windows, so it's just got half of it. So I'm sorry, and I will write the show notes for it.
What happened?
I made a mistake.
Oh, what happened?
I think it went off.
I didn't put the record.
So how much is missed?
Like 20 minutes. 20.
Okay. Well, I have the notes at least, and a lot of these today. This example, the project selection example, is from the Ericsson notes. So you have the entire workload example in there as well. So you won't lose too much from that.
Yeah.